Section 4.3, increasing, decreasing, concave up, concave down. Take a review first about what we learned in the last class. We learned two theorems in the last class, Rolle's theorem and the mean value theorem. Rolle's theorem. If a function is continuous on a closed interval, differentiable on this open interval, and function value at the two endpoints are equal, then there is a c in this open interval such that derivative at c is 0. Open interval doesn't contain the endpoints, so c is in this open interval. That means that c is greater than a less than b. C is between a and b. We have two graphs here, but the left one doesn't satisfy the conditions of Rolle's theorem. Doesn't satisfy all the conditions of Rolle's theorem because this curve has a corner. At the corner, the function is not differentiable. So violate this condition, differentiable on everywhere on this open interval. So this curve doesn't satisfy all the conditions of Rolle's theorem. But this curve does. So you can find at least one point C. Their derivative is 0. This is calculus language. In geometrical language, a function is a curve, differentiable everywhere on this open interval. That means that over this open interval, the curve has no corner. In other words, the curve is smooth everywhere. So in geometrical language, Rolle's theorem is like this. If a curve, a function, is continuous, smooth, low corner, derivative exists, and the two endpoints of the curve, they have the same height, function value are equal, then at least one tangent line is horizontal. Derivative is slope of a tangent line. Derivative is 0. That means that tangent line is horizontal. This curve is not smooth everywhere between A and B. So you cannot find a tangent line on this curve. There, the tangent line is horizontal. You cannot find horizontal tangent line about this curve because there is a corner that doesn't satisfy the conditions of the theorem. No guarantee there is a horizontal tangent line. About this curve, continuous and smooth, and also the two endpoints, they have the same height. So at least one tangent line is horizontal. Yes. The mean value theorem. In calculus language, if a function is continuous on this closed interval, continuous, and differentiable on this open interval, not this curve. This curve has a corner. So this curve is not differentiable everywhere. But this curve is differentiable everywhere on this open interval. Then, conclusion, there is at least one C inside this open interval such that derivative at C is this number. This number is the slope of the line that join the two endpoints. Yeah, this broad line, by the slope formula, you will see the slope of the broad line is this number. Yeah, the slope of this broad line is this number. This curve doesn't satisfy the function, doesn't satisfy smooth everywhere over the interval AB. So this curve, you cannot find a C where the derivative is equal to this number. Derivative is slope of tangent line. This number is slope of the broad line. Slope is equal to slope. That means that tangent line is parallel to the broad line. So on this curve, you cannot find a tangent line that is parallel to the broad line, because this curve has a corner, not differentiable everywhere. This is the calculus language about this theorem. In geometrical language, this theorem is if a curve is a function is curve. If a curve is continuous and smooth everywhere, no corner, then at least one tangent line is parallel to the line that join the two endpoints. The line that join the two endpoints, this line. So at least one C where tangent line is parallel to the broad line. This is a review about what we learned in the last class. Now today's topic, increasing, decreasing concave arm and concave down. Here we have a curve. This is the graph of some function. This curve is increasing from point A to point B, then decreasing from B to C, and then increasing again. Now consider this portion of the curve. I draw some tangent lines to this curve, to this portion. Then it's easy to see that each tangent line has positive slope. So when a curve is increasing, slope everywhere is positive. This portion from B to C is decreasing. If you draw tangent lines, each tangent line has negative slope. So when a curve is decreasing, slope everywhere is negative. From this observation, we have the following theorem. We call this theorem increasing, decreasing test. You can find this theorem on this page. Part 1. A function is increasing. A function, f of x, a function. This is a calculus language. Geometrical language is a curve. A function is a curve. A curve is a function. A curve is increasing on some interval. Then derivative is a calculus language. Geometrical language is slope. Then slope is positive everywhere on the interval. The reverse is also true. If slope is positive everywhere on some interval, then the graph, the curve, is increasing on the interval. Similarly, a curve is decreasing on some interval if and only if slope is negative on the interval. This is about increasing, decreasing. Now, concave up and concave up, concave down. Here we have two curves. They bend in different directions. This curve bends upward. This curve bends downward. We also call this curve concave up, this curve concave down. Let's examine concave up first. Again, I draw some tangent lines. Now, guess on the slopes of the tangent lines. About this tangent line, slope is negative, about negative 0.5. This tangent line, the slope positive, about 0.7. This tangent line, the slope is positive, larger, about negative 2, for example. So when you draw some tangent lines, then you will see the slope of the tangent line is increasing. When tangent line is close to the point A, large negative, then small negative, then about here, slope 0. Then beyond the point, positive, large positive, very large positive. So the slope is increasing. So here, I plot the graph of slope or plot the graph of derivative. Yeah, close to A, large negative, then small negative. Then at some point, slope is 0. The point is about here. Tangent line, the slope is about 0. Then beyond this point, slope positive, small positive, then large positive. So when a curve is concave up, if you plot the graph of slope, you will see the curve is increasing. By increasing, decreasing test, when a curve is increasing, the slope of the curve greater than 0. So this curve is increasing. So the slope, if you draw tangent line everywhere, slope is positive. Slope of this curve is derivative on this guy. That means that second derivative of f. Based on this observation, we have part 1 of this theorem. This theorem is called concavity test. You can find this theorem on this page in the book. Part 1. A curve is concave up on some interval. Concave up on some interval. Then the slope of the curve is increasing on the interval. Yeah. If you plot the graph of slope, then you will see slope is increasing. Therefore, by increasing, decreasing test, a curve is increasing. Slope of this curve, positive. This curve is the graph of this guy. Slope of this curve, take derivative on this guy, second derivative greater than 0 on the interval. So a curve is concave up. Then first derivative increasing, second derivative greater than 0. The reverse is also true. Second derivative greater than 0. Second derivative is slope of this guy. Second derivative greater than 0. So this guy increasing. This guy is first derivative. First derivative is slope of f. So slope increasing. negative, small negative, 0, small positive, large positive. So the curve, the original curve, the graph of f must be concave up. Because the slope is increasing, the graph of f must be concave up. So the reverse is also true. Second derivative greater than 0. First derivative increasing. And the original f is concave up. Now examine concave down. Again, draw some tangent lines and examine the slopes of the tangent lines. Say this tangent line slope positive, quite large. Say positive 3. The slope of this tangent line is positive, but smaller, about positive 1. If you draw a tangent line here at this point, you will see slope 0. And this tangent line, slope is negative, but small negative. If you draw a tangent line close to the point B, slope negative, but large negative. Now, I plot the graph of slope of this curve, or plot the graph of derivative of g. Close to A, large, positive, then small, positive. Then at some point, 0, slope is 0. This point, yeah, slope is 0. And then beyond the point, negative, large, negative, negative, large, negative. So when a curve is concave down, slope actually is decreasing. So by increasing, decreasing test, when a curve is decreasing, slope of the curve negative. So slope of this curve negative. Slope of this curve is derivative on this guy. That is second derivative of g. So when a curve is concave down, second derivative less than 0. So we have the second part of concavity test. A curve is concave down. Then slope of the curve is decreasing. Yeah. Slope of the curve decreasing. Large positive, small positive, 0, small negative, large negative. Its graph is here, decreasing. Yeah. This guy is decreasing, so slope of this guy, that means that take derivative on this guy. Second derivative of the original f, less than 0. Decreasing, then slope less than 0. Yeah. The reverse is also true. Second derivative less than 0, the first derivative is decreasing. First derivative is the slope of the original function. Slope decreasing, then fourth, the original function, its graph is concave down. So slope decreasing, graph, original function is graph concave down. So in summary, a curve is increasing, then if and only if derivative greater than 0. A function is decreasing if and only if derivative less than 0. So first derivative controls increasing, decreasing. On the other hand, second derivative controls concave up and concave down. A curve is concave up if and only if second derivative greater than 0. A curve is concave down if and only if second derivative less than 0. So keep that in mind. First derivative is about increasing, decreasing. Second derivative is about concave up, concave down. Now, let me show you examples. Example 1. We are given the graph of some function f of x. Now, based on this diagram, answer some questions. First question, find the open intervals on which the function is increasing. So where the function is increasing. From 1 to 3, the curve is increasing. From 4 to 6, the curve is also increasing. So the answer to this question is the open interval 1 to 3 and 4 to 6. Second question, find the open intervals on which f is decreasing. The graph is decreasing. Between 0 and 1, from 0 to 1, the curve is decreasing. From 3 to 4, the curve is also decreasing. So the answer to the second question is the interval 0 to 1 and 3 to 4. 3 to 4. The third question, find the interval on which the function is concave up. Now examine the graph of the function concave up, where the graph is concave up. I can see that this portion is concave up from this point. To this point, concave up. Then the other part, the other parts are not concave up. So the answer to the third question is which open interval on which the function is concave up? The answer is 0 to 2. 0 to 2, concave up. D, find the open intervals on which the function is concave down. Concave down, I can see that from 2 to 4, the curve concave down. Then 4 to 6, also concave down. So the answer to D is open interval 2 to 4 and the open interval 4 to 6. Question E, find the x coordinates of the points of inflection. First, you need to know what is a point of inflection. Here is the definition. A point on a curve is called a point of inflection if the curve is continuous and the curve changes concavity there. Change concavity there. That means that change, say, from concave down to concave up, or from concave up to concave down at the point. Then the point is a point of inflection. Okay. A point has x and y coordinates. Part E only requires us to tell the x coordinates of the points of inflection. So go back to the graph. At which point on the graph concavity is changing, I can see that at this point. Yeah, at this point, the curve changes from concave up to concave down. So this point on the graph, the point is a point of inflection. Its x coordinate is 2. So the answer is the x coordinates of the point of inflection is 2. How about this point? This point is not a point of inflection because on the left, the graph is concave down. On the right, to this point, the graph is also concave down. So at this point, the graph doesn't change concavity. Therefore, this point is not a point of inflection. Example 2. Sketch a possible graph of a function. The function satisfies the following conditions. This example is a typical exam problem. If you look at the past exam fee, almost each past exam fee contains one problem like this. Okay, now to sketch the graph of this function, let me draw an XY plane. Okay, now let's go through the conditions one by one and mark down the information on the XY plane. Okay. First condition, derivative of the function greater than 0 on this interval from negative infinity to 1. By increasing decreasing test, when first derivative greater than 0, the graph of the function is increasing. So mark down this information. From negative infinity to 1, the curve, the graph of the function is increasing. So I mark down the information from negative infinity to 1. The curve is increasing. First derivative less than 0 on 1 to infinity, this interval. From 1 to infinity, first derivative less than 0. That means that the graph of the function is decreasing. So from 1 to infinity, curve is decreasing. Mark down the information. Okay, now this condition. Second derivative, remember, second derivative is about concave up and concave down. Second derivative greater than 0 on this interval. On this interval. Greater than 0 is concave up. So from negative infinity to negative 2, the graph of the function is concave up. Mark down the information. Concave up. And also second derivative is greater than 0 on this interval, 2 to infinity. So 2 to positive infinity, the curve also concave up. Second derivative greater than 0, concave up. Second derivative less than 0 on this interval. So between negative 2 and 2, second derivative less than 0, the graph is concave down. Between negative 2 and 2, the graph is concave down. Mark down the information. Now, the third condition. When x approaches negative infinity, the function approaches negative 2. So negative 2 is a horizontal tangent line. So suppose this point is negative 2. I draw a horizontal line. This line should be horizontal asymptote. When x approaches positive infinity, the function approaches 0. So 0 is a horizontal asymptote. 0, that means that the x-axis, it is a horizontal asymptote. Okay, now let's sketch a possible graph. Piece by piece. The first piece is negative infinity to negative 2. On this interval, the graph should be concave up and increasing, and this horizontal line is a horizontal asymptote when x approaches negative infinity. So when x approaches negative infinity, the graph should be closer and closer to this horizontal line and concave up and increasing. So the graph looks like this, concave up and increasing. Now, second piece. From negative 2 to 1, over this interval, the graph is concave down and increasing. So concave down and increasing. So I draw the curve like this, concave down, but increasing. Stop here. The third piece. The third piece, I draw the graph over this interval, 1 to 2. Between 1 and 2, the graph concave down, but decreasing. So concave down, but decreasing. The last piece is a 2 to infinity. 2 to infinity, the graph should be concave up, decreasing, and approaches 0 as x approaches infinity. So the graph looks like this, decreasing, but keep the curve concave up and get closer and closer to the x-axis. So this red curve is a possible graph of the function that satisfies these given conditions. The third example. This example has 5 questions. Let's answer the questions one by one. Consider the curve given by this function. The first question, find the intervals on which the curve is increasing, decreasing. Recall that increasing, decreasing, they are determined by first derivative. First derivative greater than 0, increasing. Less than 0, decreasing. Okay, now I compute derivative on this function. It is this. To find intervals on which derivative is positive or negative, increasing or decreasing, I first find points where derivative is 0 or doesn't exist first. Because derivative is a polynomial, it has low denominator, so derivative exists everywhere. Derivative doesn't exist at the point where denominator is 0, but low denominator, so derivative exists everywhere. So low point can make derivative doesn't exist. Now I want to tell the points where derivative is 0. Set derivative to 0 and solve the equation. The left hand side is derivative. Solve this equation. factorization. And then we can see that when x is 0 and free, derivative is 0. So we get 2 points. Okay, derivative is 0 only at these 2 points. At other points, derivative cannot be 0. Now I use these 2 points to cut the domain of the function. Why cut the domain of the function? Because outside the domain, the function has no graph, so we don't need to consider points outside the domain. The domain of a polynomial is any number from negative infinity to positive infinity. So I draw a number 9. A number 9 is any number from negative infinity to positive infinity. Now I use these 2 points to cut the number 9. Then we have 3 subintervals. 3 subintervals. Negative infinity to 0, 0 to 3, and then 3 to infinity. To determine first derivative is positive or negative on each of these 3 intervals, I say to determine the sign of first derivative on this interval, I arbitrarily pick a point, say -1 from this interval, and evaluate first derivative at -1. That means that plug in -1 in x here. So we get derivative at -1 is 4 times -1 to the third minus 12 times -1 squared. I get -16, less than 0. So over this interval, derivative is less than 0. And therefore, derivative is the slope of the graph of f. So the graph of f is decreasing. Slope everywhere less than 0. The graph must be decreasing. Now, second interval. To determine the sign of derivative, I arbitrarily pick a point from this interval, say pick 1. Plug in 1 in x here. Derivative at 1 is 4 times 1 to the third minus 12 times 1 squared, -8. Oh, less than 0. So on this interval, derivative less than 0. Derivative is slope. Slope of a curve less than 0. So the curve decreasing. The third interval, 3 to infinity. Arbitrarily pick a point, say pick 4. Then evaluate derivative at 4. I get 64 greater than 0. So on this interval, derivative greater than 0. Slope greater than 0. Everywhere, slope greater than 0. So the graph increasing. So the answer to the first question, find intervals on which the curve is increasing or decreasing. The answer is over this interval, curve decreasing. On this interval, also decreasing. On this interval, the curve increasing. Second question. Find the local maximum and minimum function values. Second question is easy to answer because we have solved the first question. I can roughly sketch the graph of the function f based on this information. From negative infinity to 0, from negative infinity to 0, the curve decreasing. From 0 to 3, curve decreasing again. From free to infinity, the curve increasing. I should say that this is only a rough sketch of the graph of the function, just for answer the second question. This curve is clearly not accurate. Now, from this rough sketch of the graph of the function, I can tell that at 0, this point is not a local maximum, not a local minimum. Locally, this point is not the highest point, nor the lowest point. At the point 3, I can see that the curve has a local minimum at point 3. So the answer to the second question is local minimum function value is negative 27, where when x is 3. Function value at 3, locally, it is minimum. How to get function value at 3? Plug in the number 3 into the original function. 3 to the 4th minus 4 times 3 to the 3rd, negative 27. The function has low local maximum. Low point is maximum locally. So this is the answer to the second question. Now, question 3. Find the intervals on which the curve is concave up or concave down. Concave up, concave down. You need to consider second derivative. Second derivative greater than 0, the curve concave up. Second derivative less than 0, the curve concave down. So to answer the third question, I compute second derivative. Take derivative on the first derivative. Take derivative on this guy to get second derivative. To find intervals where second derivative is greater than 0 or less than 0, I suggest find points where second derivative is 0 or doesn't exist. Because I want to use those points to cut the domain of the function into subintervals. Second derivative is a polynomial. It has low denominator. So second derivative exists everywhere. Only at points where denominator is 0, second derivative doesn't exist, but low denominator. So second derivative exists everywhere. Okay, so low point can make second derivative doesn't exist. Okay, now let me set second derivative to 0 and solve this equation. Left hand side is second derivative. Now factorization. Now from here we can see that when x is 0, x is 2, second derivative is 0. Okay, now I use these 2 points to cut the domain. The domain of the function f is negative infinity to positive infinity. That means that the whole x-axis, now 0 and 2 cut x-axis into 3 subintervals. Yeah, 3 subintervals. Now let me determine the sign of second derivative on each of these 3 subintervals. For the first subinterval, I arbitrarily pick a point, say pick negative 2. evaluate second derivative at -2. How? Plug in -2 in x here. Then 12 times -2 squared minus 24 times -2. It is 36, greater than 0. So over this interval, second derivative is greater than 0. Therefore, the graph of the original function is concave up. Concave up. Now, second interval. Arbitrary pick point, say pick 1 and plug in 1 in x here. Then I get the value of second derivative at 1 is -12, negative. So on this interval, second derivative is negative. Therefore, the graph of the original function is concave down. Similarly, the third interval, arbitrary pick point, pick 3. Second derivative at 3 is 36, positive. So over this interval, the graph of the function f is concave up, concave up. So the answer to the third question is, on this interval, negative infinity to 0 and 2 to positive infinity, the graph of f concave up. And from 0 to 2, the graph concave down. Yeah, here I roughly sketch the graph of f, the original function. Let me emphasize that this is just a rough sketch, not accurate. From over this interval, concave up, infinity to 2, infinity to 0. Yeah, this is 0, 0. Concave up. Then 0 to 2, 0 to 2, concave down. Then 2 to infinity, concave up again. Question 4. Find the x coordinates of the points of inflection. Recall that a point of inflection is a point on the graph. There, the graph change concavity. At 0, the graph change from concave up to concave down. So this point is a point of inflection. The x coordinate of this point is 0. Now, the second point of inflection is this point. The curve, the graph change from concave down to concave up. So there are 2 points of inflection. Their x coordinates are 0 and 2. 0 and 2. Now, finally, sketch a possible graph of this function. Use the information that we got. Okay. Yeah. Here is the graph from the information I got from the from part 1 to part 4. I marked down the informations. From negative infinity to 0, decreasing, so I mark it down. From 0 to 3, decreasing, mark down the information. 3 to positive infinity, increasing. And from negative infinity to 0, concave up. 0 to 2, down to the infinity, up. Okay. And then I draw the graph piece by piece. When x is 0, function value is 0. So the graph passes the origin passes this point. Okay, now over this piece, over this interval, curve, concave arc, but decreasing, pass through this point. So the graph looks like this. When x is 2, plug in 2 in x, then I get the function value is negative 16. So this point is on the graph. Over this interval, the curve is down, concave down, decreasing. So the graph looks like this and stop at this point. When x is 3, plug in the number 3 in x, then the function value is negative 27 here. This point is part of the graph. It's a point on the graph. Over the interval 2 to 3, the curve, concave arc, decreasing. So concave arc, decreasing, and stop at this point. Now, the last piece of the graph from 3 to positive infinity. The graph is concave arc increasing. Now, starting at this point, draw a curve, concave arc, and increasing. So this is the graph of this function. You can have a check whether or not my sketch is accurate or not by a graphing calculator. You can plot the graph of this function by a graphing calculator and compare to my sketch. They should be very, very close. The last example today. Consider this polynomial. Question A. Find the intervals on which the function is increasing or decreasing. Remember, derivative is positive, the curve increasing. Negative, the curve is decreasing. So to answer this question, compute derivative first. To find intervals, I suggest determine the points where the derivative is 0 or doesn't exist first, because I want to use these points to cut the domain of the function into subintervals, into intervals. Again, derivative is a polynomial. It has low denominator. So low point can make this derivative doesn't exist. To find the points where derivative is 0, I set derivative to 0 and solve this equation. Left-hand side is the derivative. Now solve this equation. You can use factorization, but I like to use quadratic formula. Then quadratic formula, negative b plus minus square root b squared minus 4ac over 2a. The answer is negative 1 and 0.5. So 2 points, their derivative is 0. Derivative is 0 only at these 2 points. Now I use these 2 points to cut the domain of this function into intervals. The domain of this function is the whole number 9 from negative infinity to positive infinity. Now 2 points cut. Then I get 3 intervals. Yeah. free intervals. Okay, now let's determine the sign of derivative on each interval. From this interval, I arbitrarily pick upon, say, pick -2 and compute derivative at -2. Plug in -2 in x here. Then I get 30. So derivative greater than 0 on this interval. Therefore, the original function is increasing on this interval. Second interval, arbitrarily pick upon, I pick 0. Plugging 0 in x here, then derivative at 0 is -6, less than 0. So derivative on this interval less than 0. The graph of the function, original function, decreasing. Similarly, on this interval, the graph is increasing. So the answer to question A is over this interval and this interval, the graph, the function f is increasing. On this interval, the function f is decreasing. Question B. Find the local maximum and minimum values of the function. To answer this question, use the information that we obtain from part A. I roughly sketch the graph of the function. This is only a rough sketch, not accurate. I sketch this graph only for answering question B. Okay, now from the information here, from -infinity to -1, the graph of f increasing, so increasing. And then -1 to 0.5, decreasing, decreasing. 0.5 to 8 to infinity, increasing again, increasing again. So from this rough sketch, I can tell that the function has a local maximum at -1 and has a local minimum at 0.5. So the answer to B is local maximum is at 1, function value at 1. Local maximum function value is f of -1. How to get f of -1? This is a f, function f. Plug in -1 in x. Yeah, so yeah, this rotation is plug in -1 in x to get this. And then 6 is the function value of f at -1. 6 is a local maximum function value. And the local minimum function value is function value at 0.5. How to get 0.5? Plug in 0.5 into the function, yeah, into the function. This is the function f. Okay. Then I get -0.75. So -0.75 is a local minimum function value, where the location is at x is 0.5. When x is 0.5, the function has a local minimum function value, -0.75.